Chapter 1 Solid States. Based on the intermolecular force of attraction, matter can be classified into three. Intermolecular force of attraction അനുസരിച്ച് മാറ്ററിനെ മൂന്നായി തരംതിരിച്ചിരിക്കുന്നു. Solids, liquids and gases. General characteristics of solid state. Constituent particles are closely packed. The intermolecular force of attraction is very small. The intermolecular distance is very low. Solids are rigid. Solids are incompressible. Solids have definite mass, shape, and volume. Classification of solids. Based on the mode of arrangement of constituent particles, solids can be classified into two: crystalline solids and amorphous solids. Crystalline solids. The solids in which constituent particles are arranged in regular orderly manner is called as crystalline solids. It has a definite geometrical shape. It has a long range. It has a sharp melting point. It has a definite heat of fusion. They have anisotropic nature. It cleaves along a definite plane. They are also called as true solids. Examples of crystalline solids: rock salt, diamond, graphite, ice, all the metals except mercury. Amorphous solids. The solids in which constituent particles are arranged in irregular manner is called as amorphous solids. It does not have a definite geometrical shape. It has a short range. It has a range of values as melting point. It does not have a definite heat of fusion. They have isotropic nature. It cleaved along an irregular plane. They are also called as pseudo-solids or supercooled liquids. Examples of amorphous solids: glass, starch, protein, wood, rubber, and rock. Anisotropic and isotropic nature. Some of the solids shows different physical properties against external force from different directions. This phenomenon is called as anisotropic nature. Some of the solids shows similar physical properties against external forces applied in every directions is called as isotropic nature. Classification of crystalline solids. Based on type of constituent particles, crystalline solid can be classified into four: molecular crystalline solid, covalent crystalline solid, ionic crystalline solids, and metallic crystalline solids. Molecular crystalline solids. Crystalline solids in which molecules are acted as constituent particles is called as molecular crystalline solids. The binding force between constituent particles in molecular crystalline solid will be van der Waals force. Based on type of molecules, molecular crystalline solids can be again classified into three: non-polar molecular crystalline solids, polar molecular crystalline solids, and hydrogen bonded molecular crystalline solids. B. Covalent crystalline solids. The crystalline solids in which covalent bonded atom acted as constituent particles is called as covalent crystalline solids. The binary force will be covalent bonds. Some of them are hard, but others are soft. Some of them are conductors and others are insulators. They have fairly high melting point, example diamond and graphite. Ionic crystalline solids. The crystalline solids in which ions are acted as constituent particles is called as ionic crystalline solids. The binding force will be electrostatic force of attraction. The ionic crystalline solids are hard but brittle. At solid state they are insulators, but at molten or aqueous state they are conductors. They have high melting point. Examples: sodium chloride and zinc blend. Metallic crystalline solids. The metallic solids in which cations and free electrons are acted as constituent particles is called as metallic crystalline solids. The binding force will be metallic bond. They are hard and they show properties like malleability and ductility. Their melting point are very high. They are good conductors. Examples: iron, copper, zinc, aluminium, X. Crystal lattice. The regular three-dimensional arrangement of constituent particles in a crystalline solid is called as crystal lattice. The smallest repeating part of a crystal lattice is called as unit cell. Types of unit cells. There are mainly two types of unit cells: primitive unit cell and centered unit cell. Primitive unit cell. The unit cell which consists of constituent particles only at 8 corners is called as primitive unit cell. Centered unit cell. The unit cell which consists of constituent particles other than corners is called as centered unit cell. There are three types of centered unit cells: body-centered unit cell, face-centered unit cell, and end-centered unit cell. A. Body-centered unit cells. Unit cell which consists of constituent particles at 8 corners and body center is called as body-centered unit cell. B. Face-centered unit cells. The unit cell which consists of constituent particles at all 8 corners and all the faces is called as face-centered unit cell. C. End-centered unit cell. The unit cell which consists of constituent particles at 8 corners and any two opposite faces is called as end-centered unit cells. Number of constituent particles in a unit cell. Corner of a unit cell consists of 1/8 of a constituent particles. One face of a unit cell consists of 1/2 of a constituent particles. The number of constituent particles in a primitive unit cell equal to 8 into 1/8 equal to 1. Total number of constituent particles in body-centered unit cell equal to 8 into 1/8 plus 1 equal to 2. Total number of constituent particles in face-centered unit cell equal to 8 into 1/8 plus 6 into 1/2 equal to 4. Total number of constituent particles in end-centered unit cell equal to 8 into 1/8 plus 2 into 1/2 equal to 1 plus 1 equal to 2. Byeeee lattice. There are 14 different types of crystal lattices. They are collectively called as Byeeee lattice. Next topic: close packing. The process of arrangement of constituent particles in a crystalline solid with a minimum vacant space is called as close packing. There are three types of close packing: one-dimensional close packing, 2-dimensional close packing and 3-dimensional close packing. 1-dimensional close packing. The close packing of crystalline solids in which consistent particles are arranged side by side to form an edge of a crystalline solid is called as 1-dimensional close packing. Coordination number is 2. 2-dimensional close packing. The close packing in which we are discussing about formation of one layer of a crystalline solid by the arrangement of rows side by side is called as 2-dimensional close packing. There are two types of 2-dimensional close packing: square close packing and hexagonal close packing. A. Square close packing. The 2D close packing in which all the constituent particles are arranged in same alignment in both row-wise and column-wise is called as square close packing. Coordination number is 4. Hexagonal close packing. The 2-dimensional close packing in which consistent particles of a row placed at depression of adjacent row is called as hexagonal close packing. The coordination number is 6. 3-dimensional close packing. The arrangement of layers of constituent particles one above the another to form a 3-dimensional structure of crystalline solid is called as 3-dimensional close packing. There are two types of 3-dimensional close packing: hexagonal close packing and cubic close packing. A. Hexagonal close packing. The 3D close packing takes place by the arrangement of layers in AB manner is called as hexagonal close packing. B. Cubic close packing. The 3D close packing takes place by the arrangement of layers in ABC manner is called as cubic close packing. Continuation in part 2 video. Please like, share and subscribe my channel. Thanks for watching.